Right now we're going to be talking about the average value, and we're going to be learning an equation for the average value, but hopefully developing more than just an equation, but a real understanding of what the average value is. And we talk about the average value of a function, and what the average value is telling us is it's the average y value over a given interval. So over the interval from x going from a to b. So we're looking at the average value of a function, and before we start doing any work with that, let's really sort of get a conceptual understanding and hope that this drives our understanding of the topic. Let's think about this. Um, let's say that I have y times x, and then I divide it by x. Now, what does this equal? Well, we know what that equals. We've got an x on the top, x on the bottom. It equals just y. Well, the average value really just uses this idea. So let's think about this. Let's say that I have some function, and I'm looking at the average value of y. So the average value of y over the interval, let's say from like 2 to 7. And that could be any interval, but let's just say 2 to 7. So here's my function f of x, and I'm looking at the average value of y over the interval from 2 to 7. Now, if you look at think about our function, our y value is changing. It's going down. Now our y value is going back up. So we want to know what is our average y value over that entire interval. Maybe just to make this like a little bit more um, extreme, we could, let's put 7 over here so that we really see now y is getting bigger and bigger and bigger and bigger. So the y values change over that interval. What is the average y value? Well, think about this. Here's my x value, here's my y value. What if I found that area? And that area is just the product of all of, these rectangles, where this is my y value and that's my little delta x value. And so that this area, the area is the product of x times y. But we know a more sophisticated way of talking about that area. The area underneath the curve is the integral, in this case from 2 to 7, from x equaling 2 to x equaling 7, of f of x dx. This definite integral, that is my area, x times y. And that'll give me the total area in blue. That gives me this entire blue shaded area. But what I'm looking for is what's the average y value over that interval? Well, the area is x times y. So what I can do then is think about, you know, if I take x times y, my area, and divide it by the total x value, I'm going to get my average y value. So if I take this total area that's in boxed, if I take this total area from 2 to 7 of f of x dx and divide it by my x value, which is 7 minus 2, this will give me my y average. In other words, we can extend this and say the interval from a to b of f of x dx divided by b minus a, which is my x value, equals my y average, or the average value of a function over the interval b to a. Well, let's see that. Let's see that in action. So here we've got a velocity and time. We've been working a lot about that on these two topics. It says how far did the car travel in the first 5 hours? Well, we don't have a function, so best idea to do is Riemann sums. So let's do a Riemann sums with n equals 5, and we could use right, left, or midpoint. Let's just use a right bound. So we know the process now. So at 1 hour, I go to my, in between 0 and 1, I go to my right bound, and I make a rectangle that's 60. And granted, we see that there's some over approximation. All this green area shouldn't be there, but we're doing a Riemann sum, so that's okay. From 1 to 2, I choose my right bound, and the height is roughly like 70.1 or 71 maybe, so we could say this is 71. And then from 2 to 3, use my right bound, and that's roughly, I don't know, like 66. From 3 to 4, choose my right bound point, make a rectangle, that's roughly 50. And then from 4 to 5, choose my right bound, draw my rectangle, and that's roughly 40. So how far did the travel go in the first 5 hours? Using a Riemann sums with n equals 5 and using a right bound, it's just the sum of all of these. If I can add, right, I think that this should sum up to 287, and we're going miles per hour in hours, so this is 287 miles. So then it says, well, what's the average velocity of the car in the first 5 hours? We just found the distance that we went. We went 287 miles, and this is approximated, and we did it in 5 hours. So our average velocity over that time is just 287 miles divided by 5 hours, or 7.4, I think it is, miles per hour. And what we did there is we just used that average velocity equation, or the average value equation that we were talking about before. What we did is we said, this number here really comes from the integral from 0 to 5 of my function, velocity function, so f of x dx. It's the area underneath that curve from 0 to 5. And so that green value, that integral sign is the 287. And then we're dividing that area by the time, 5 minus 0. So when we divide the total area, which is miles, divided by the time, we get the average value, and this is the average y value over that interval. So here's our average value of f, written once again. It's 1 over b minus a, and that's my change in x. So I'm dividing by my x value multiplied by our area function. Okay, so just to sort of see an application problem, given the same setup, we've got a car going, its velocity is changing, it starts at noon, and it goes on for a while. And what we want to answer is this question. We want to say, suppose a truck starts at 1 p.m. from the same place and travels at a constant velocity of 50 miles per hour. When does the truck overtake the car? And I want to develop this in a very graphical depiction. So the truck starts at 1 p.m. So at 1 p.m. it starts, and it's going 50 miles per hour the entire time. So if we go up to 50, here's my truck. And during, let's see, the green area that I'm drawing is the green area is the distance that the car goes. And we're going to say the blue area is the distance that the truck goes. And we now understand about integrals that the distance, when we're talking about a velocity time graph, the distance is the area under the curve. So the truck, this is all the distance the truck has gone, from 0 to 4.5 miles, 0 to 4.5 hours, or rather from 1 to 4.5 hours. And during that time, the car has gone more distance because the car has also gone that distance plus all this additional distance. Okay, and at this time, at the time 4.5, this is the point right here. This is a very critical point. At that point, the car is slower than the truck. It doesn't mean that their distances are equal, but that is the point where the car starts to become slower than the truck. Therefore, the truck starts to catch up with the car. So all of, at this point, here's my car's additional distance, after 4.5 hours. It's the area underneath the curve. But the truck is also doing that distance plus this area here. And so what we need to do then essentially is match all of these boxes. That was a distance that the car did that the truck didn't do. And now it's matched. Now the truck has made up that distance. Here is a distance that the car went that the truck didn't go. And now the truck has done that. So if we just match up all these boxes, what we'll do is be able to find out the time. We'll find out when the truck catches up to the car or when their distances are equal. So I'm just going to go ahead, all of these boxes that I'm finding are on the left of this line, of this red line here. All these boxes here were distances that the car went that the truck didn't. And now to the right of the red line being when the truck is going faster. Now this is the car, sorry, rather, this is the truck catching up to the car. So just filling in these boxes, matching them up. So there's a partial box. It's not exact. It's, there's a lot of error to it. But we're just getting a rough approximation. So this box here is roughly like these two boxes. And here we go, sort of just matching up the truck catching up with the car in terms of filling in boxes. So let's see, this distance there is roughly that distance there. This distance is kind of like that distance. And we're almost now we're at the point where there's no more distances that the car went to the left of this line that the truck didn't go to the right of this line. So therefore, roughly around, between 8 to 9 p.m., the truck catches the car. And that happens because each distance, so the area under each curve, each distance is equal. In other words, at that point, the total blue distance is roughly equal to the total black distance. Sorry, I should have used green. That's what I was using. Its total is equal to the green distance there. So in other words, around 8 to 9 p.m., the green area between 8 to 9 p.m., the green area equals the blue area, which means that the distances that they've gone is the same, which means that the truck catches up to the car and overtakes it. So I'm going to pause this and we're going to start another video in just a second. Good.